Hello guys, welcome back. So today we're going to move into conditional statements. We're actually going to be done with the unit by Friday. So today we're going to do conditional statements with converse, inverse, and contrapositive. And tomorrow we'll do biconditional statements, which are a difference between definitions and descriptions. I really enjoy that day. Then on Thursday we're going to do law of syllogism and detachment, which is really simple. And then the last thing on Friday, we'll take the practice test. So we'll post the solutions to practice test on Saturday, and then we'll be ready to review on Monday, and then take the test on Tuesday. So make sure you have all of your Unit 2 or your Chapter 2 or whatever Unit 2 stuff done by next Tuesday, because that will be the deadline. This should be a pretty easy test. So if you did do as well as you wanted to on the last unit, just make sure you know how to do this stuff. Make sure you study the practice test and take it on Friday, and look over the solutions over the weekend, and we can raise your grades, okay? Also, we just got good news that we are going to go back in person after fall break. Unfortunately, it's going to be doing block schedule, so I will see you guys 2 days of the week instead of all 5, but it's better than what we're doing now, and at least then I think it'll give you guys a break. It's better for you guys. It'll be much harder for the teachers, but it'll be good for you guys because it'll give you a bit of a break between having to do entirely virtual learning to only having to do 3 days, 3 days of the week virtual distance learning. Alright, so let's go ahead and get right into it. Conditional statements. So this is an example of a conditional statement. Conditional statements have conditions to them. For instance, if we say, if it rains, then the game will be delayed. So it's kind of like cause and effect. So the condition is that it rains, and then the outcome in that case would be that the game is delayed. So our condition is if it rains, the outcome would be that the game would be delayed. So there's actually a lot of things in logic, kind of like cause and effect, that can be written as conditional statements where we have a condition and an outcome. Now typically instead of saying condition, we call this the hypothesis. So kind of like hypothesis testing, where in science you make a hypothesis or a claim, right? And then the outcome is also usually called the conclusion. So our hypothesis is that it rains, our conclusion is that the game will be delayed. So talking about conditions, it's kind of funny, maybe we can talk about unconditioned, so unconditional love. So, for instance, if someone says, I love you forever, you would assume there were no conditions to their love. But let's think of this, let's think of this a little bit more. So, are they really saying that I love you forever no matter what? If they did, that would mean that there were no conditions, right? But what actually really happens is, I will love you as long as, and then insert all the conditions. Right, and that's why we have all the divorce. So sad, so sad. Because there were conditions there. They just lied and they said that they would love you forever, but they have conditions. But your parents will always love you, even if you're a terrible, evil person. Your parents will always love you. So their love is unconditional. Other people, they're flaky, especially high school boys. Alright, so if you are perfect, then I will love you. That's really kind of what it comes down to. My love is conditional on you being perfect. Not mine, but I'm just saying that seems to be, how things. I would not take my advice on love. How about that? Let's just move on. Alright, so let's write some things as a conditional statement. So typically we write conditional statements as if-then format, but there are conditional statements that we actually have in everyday life. We just don't put them in if-then format. So I will do well on test if I study. So the key word here is the if. So kind of what we're doing is we're just switching the order of the clauses here. So if we want to rewrite this as a conditional statement, we would say, if I study, then I will do well on the test. So sometimes they are flipped. The key is really just to look for the if, and if you see the word if and it's in the second half, that tells you that's the hypothesis, and your conclusion is what you started out at. So no big deal. So over here we have our hypothesis, and then following then we have our conclusion. There's also other ways that we have conditional statements that don't even have the word if in it. So for instance, if we say all fish live in the water, so what we're saying is if it is a fish, then it must live in the water. So if it's true that all fish live in water, that's equivalent to saying if it is a fish, then it must live in the water. Again, we have our hypothesis over here and our conclusion over here, following the then. So sometimes in logic, especially when we're going to be talking about the converse, inverse, and contrapositive, it's easier to use symbols to refer to your hypothesis and your conclusion. So the symbols that we use in logic often are P and Q. So the P is going to, it stands for proposition, I believe. So like for instance, I have a proposition for you. Basically it's kind of saying like the hypothesis, but it's saying like, so if it meets these conditions, then the conclusion will happen. So anyway, P is going to be the proposition. So if it's a fish, that's a proposition. Then our conclusion or quotient, which is not like division quotient, it's just another quotient, I guess, which is what the Q stands for, will give you then it lives in the water. So proposition is that's a fish. The quotient is that it lives in the water. So if P, then Q. So often we can write it as just simplified. Instead of it's a fish as our proposition, our quotient is that it lives in water, which is going to be this part over here. We can simplify that as if P then Q, and there's a few ways we can write it with even more symbols instead of just P and a Q, kind of like variables. But we can actually use this arrow. The arrow tells us the direction that we're going in. So it's not saying that it's going that way, it's saying it's going to the right. So if P happens, then we follow the arrow, then the Q is going to happen as well. And we can read this as P implies Q. So the arrow symbol in logic is read as imply. So P implies Q. So if P happens, that implies that Q happens as well. And that's what's going on when we're dealing with logic. So if it's a fish, it lives in water. So that means that if it's a fish, that implies that it must live in water. So that's the arrow going that way. All right, and tomorrow we'll talk about what happens when the arrow goes both ways. And it's biconditional because it's got two conditions going both directions, and it's a definition, well defined. Alright, so visualizing conditions, we can also use Venn diagrams, which I love to do. So if we have a statement, all fish live in water, it means if it is a fish, it must live in water. So the question is, that was not what I was trying to do. The question is, here we have subsets, okay, so we have the smaller circle that lives inside of the bigger circle, and notice that the small circle is entirely inside. There's no part that's sticking out or anything like that, okay? So this small circle is a subset that lives inside the bigger set. So the question is, if we know that all fish live in water, then that means that our fish here have to live entirely inside these, be a subset of all the things that live in water, right? So whenever we write this, it's going to be P and Q. And that didn't happen. I don't know. Anyway, but the point that I'm trying to make here is that there are other things that live in water that are not fish, such as you see there, whales, right? So by the way, that was the one I was looking for. Darn. So in general, we can say P implies Q means P is a subset of Q as well, okay? Whether it's a proper subset, we'll talk about that tomorrow. So anyway, there are other things that live in the water that are not fish, like whales or any other mammals. We also have Ariel, right? Ariel lives in the water, but she's only half fish, so I guess perhaps she goes like right there. I don't know. It gets confusing. Disney's messing me up. Alright, so here's another one. Spinach makes you strong. So we have subliminal messages, right? So all of Popeyes, the suggestion is that if you eat spinach, then it'll make you strong. And in Popeye's imaginary world, every time he eats spinach, he becomes instantly strong, right? So the statement is that spinach makes you strong. And let's just assume, just for the sake of these slides, that this is true, that this magical spinach will make you instantly strong. Obviously, I don't eat a lot of spinach. Alright, so the question is, how would we rewrite this as a conditional statement? So if you eat spinach, then you'll be strong, right? So our hypothesis is that you eat spinach, or our proposition, or proposition, and then the conclusion or the outcome would be that you will be strong. So let's visualize that. So people who eat spinach are going to be a subset of the people who are strong. So spinach is going to be the subset here of all the people who are strong. Now again, there are people who eat spinach, at least in this fantasy world or whatever, is going to be, we're going to say if this is true, then spinach eaters are a subset of the people who are strong, because everyone who eats spinach would have to be strong in that case. But there are other people who are strong who do not eat spinach, right? For instance, you could work out. I'll work out. Anyway, you don't even know what that is. Don't look at that body. You could lift weights. Do you even lift, bro? Pretty much. Obviously, I don't. And then the next question is, where does Popeye live? So in this little setting here, we have people who are strong. Clearly, Popeye is strong. Then we have people who eat spinach. Clearly, Popeye eats spinach. So he would actually be right here. So Popeye lives inside the subset of people who eat spinach who are strong, where me I'll work out. So I'm strong, but I don't eat spinach, so I would live outside of the subset of spinach eaters. Anyway, that's how sets work in Venn diagrams. So here's another one, and we want to write it as a conditional. So all birds have wings. So if it is a bird, then that means that it must have wings. So our hypothesis is that it is a bird. Our conclusion or outcome would be that it has wings. So let's use this example to go through and learn about inverse, converse, and contrapositive. So an inverse means we're going to inverse the statement, but not switching the order. That's actually the converse. We inverse it by negating it. So this little symbol here is a tilde, so T-I-L-D-E, pronounced tilde, very similar to Matilda, which is a completely different inside joke and story. And if you ask some seniors this year, they would even tell you the story of Tilda, and there's a lovely story that goes behind it, but I am not going to put that out there for the whole world to see, but it was hilarious. And I will tell you the story, of course, when we get back in person, and we will go back in person, so this is going to be awesome. Can't wait to tell you guys all my funny stories. So anyway, inverse is going to be not P implies not Q. So now you can see why we use these symbols, because it's easy to use the symbols to show what's changing from the conditional statement to the inverse. So if our conditional is that if it's a bird, then it has wings, or in other words, P implies Q, which is right, P implies Q, then the inverse of the statement is not P implies not Q. So notice we keep the order the same as the conditional. The only thing that's changing is we're negating both of them. So if we wrote that out in words, we would say that if it is not a bird, then it does not have wings. So notice it's the same order, bird wings, as a conditional statement, but now we're just negating it. We're just adding nots in front of both the hypothesis and the conclusion. So that's the inverse of the statement. Pretty simple to do. Don't worry too much about the truth value of the statements. I know some of these are obviously not true. We're going to evaluate those in a little bit. So there's a reason that I'm making some of these that are clearly not true. Alright, then we have the converse. So when we're thinking about converse, I want you to think about the shoes, okay? And think of shoes on the wrong feet. So for the converse, the way I remember it is if you have shoes on the wrong feet, you just switch the order and you put them on the right way. So when it comes to the converse, all we're doing is P implies Q for the conditional turns into Q implies P. So we're just switching the order of the two sides, just like switching and putting shoes on the wrong feet. I said feet on the wrong shoes. Oh man, that's bad. Alright, so if it is a bird, then it has wings. That's our conditional statement. So the converse of that statement would be that if it has wings, then it is a bird. Oh, you can see the green sticking out. Alright, so anyway, that would be the converse of the statement. And again, don't worry about it not being true just yet. Now the last one we have is a contrapositive. This is the longest word. Contrapositive is longer word than converse or inverse, and so it's obviously the most complicated. So what we're going to do, if you notice here, going from P to Q to not Q and not P, is we're going to switch the order, because it's the converse, it's got the con in the converse, and we're going to negate it, so that's the contrapositive. And in fact, contra just means against, and then positive is positive. So if something is against positive, it's going to be negative, but it's also the con part, which is switching the order. So anyway, that could be some things that can help you remember it, but however you want to do it. So P implies Q. Now we're going to switch the order to Q and P, like the converse, and we're going to negate it, so it's the inverse and the converse both being applied to the original statement. So not Q would be if it does not have wings, then it is not P, which would mean that it is not a bird. And that's the contrapositive. Alright, so let's review all these that we learned together. So the conditional statement is just the regular order, P implies Q. So if it is a bird, then it has wings. The inverse of the statement, we're going to negate them, so now we have to use our tilde symbols here. So, but we keep the order the same on this one. So if it is not a bird, that means that it does not have wings. And then the converse, like shoes on the wrong feet, we switch the order. So if it, but we're not negating it, so if it has wings, then it is a bird. And the contrapositive, or CP if I abbreviate it, we're going to do both the converse and the inverse, so we switch the order and we negate them. So I'm going to go ahead and move my negation symbols here for the tildes. So if it does not have wings, then it is not a bird. Now the last thing I want to do is evaluate with the truth value. So are these statements true? So if it's a bird, does it have wings? So do all birds have wings? Yes, that is true. Okay. Then let's look at the inverse. So the inverse of the statement is that if it is not a bird, that means it does not have wings. So is there anything that exists out there that has wings that's not considered a bird? So yes, like flies or dragonflies or airplanes. There are many things that have wings that are not necessarily a bird. So this statement is actually false. And the reason it's false is because this is a description of birds, not a definition of birds. So it's not reversible. But we'll get into that more tomorrow. But yes, it is really cool. And that means that it is a proper subset instead of an improper one, which would mean that they were actually one and the same. But that's okay. So next we'll look at the converse. So that would say that if it has wings, then it has to be a bird. Is that true? No, that's not true. And if you notice these two statements, the inverse and the converse, wasn't that really asking the same thing? So if it's not a bird, it doesn't have wings. No, that's not true because there's things that have wings that are not birds, right? And then if it has wings, does it have to be a bird? No, that's not true either. So the inverse and the converse are actually logically equivalent statements. So if the inverse is false, that means the converse has to be false as well. And if the inverse is true, that means the converse has to be true as well automatically. And that's actually pretty stinking cool. Another thing I'll point out is the conditional statement is logically equivalent to the contrapositive. So I don't even have to look at the contrapositive statement to know that it has to be true as well, because it's logically equivalent to the conditional. So just as the inverse and converse are tied together, so is the conditional and the contrapositive, which is pretty cool. So let's go ahead and look at it. So if it does not have wings, that means it is not a bird. So is that true? So if it doesn't have wings, it can't be a bird. That's true because all birds have wings. If you can think through that, it is. So let me review real quick. The conditional is just P implies Q. It's in the regular order. If P, then Q. P implies Q, right? The inverse, we just negate it. So if not P, then not Q. The converse, like shoes on the wrong feet, we switch the order. So Q and P now instead of P and Q. And then the contrapositive is the longest one. We do both the converse and the inverse. So that's going to be not Q implies not P. One more thing I need to show you, then we're done, is the logical equivalence of the conditional and the contrapositive. Now I stated that those two were the same, that they were tied together, the conditional and the contrapositive. So if one of them is true, we know the other one's true as well. Alright, so to show you that, let's look at an example. So here we have P implies Q, which we could use the example of if it is 2, that's funny. So if it is 2, then it is an even number. In other words, 2 is a subset of all the other even numbers. Now, are there other even numbers? Yes, such as like 4 and 6 and all the other even numbers that are not 2, right? This is going to bother me, so I have to fix it. Okay, so then let's look at the contrapositive. So if it is not Q, then it is not P. So in other words, what does it mean to be not Q? Well, Q is even numbers, so if it's not an even number, what is it? It means it has to be an odd number. So if it lives outside of the big circle of even, then that means that it cannot be P, which is 2. So think about that for a second. If P is a subset of Q, meaning P is entirely inside Q, and then you tell me that something that's not in Q, so it's outside the big circle, that means it also has to be outside the small circle as well. So that's why those two are logically equivalent. So again, one more time, if P is a subset of Q, meaning P lives entirely inside of Q, if you tell me you have something that's outside of Q, like odd, then that means it clearly has to not be P. So that's why the conditional and the contrapositive are logically equivalent to each other. One more thing I want to show you. If the conditional and the contrapositive are logically equivalent, so if one is true, that means the other one is true as well. So let me go back to these statements over here. So what happens if we take the contrapositive of the conditional statement? So we're going to switch the order, and then we're going to negate it again. So switch the order back, which is going to give me birds and wings. And then when we negate it, we're going to have not birds and not wings. So I don't know if you caught that, but the contrapositive of the converse is the inverse, and the contrapositive of the inverse is the converse. And that's why those two are logically equivalent as well. So whether they both be true or they both be false, they're going to be tied together, just like the conditional and the contrapositive are, which is absolutely fascinating. Okay, so that's enough of that. Let's go ahead and move on to the assignment. So on number 1, we want to identify the hypothesis and the conclusion by underlining the hypothesis once and the conclusion twice. So key is to look for the if. Okay, that's going to tell us what our hypothesis is. So if a number is divisible by 2, that's our hypothesis. Alrighty, then that means that the number is even. I should really redo the animations. So the number is even is going to be our conclusion. The dog will bark if a stranger walks by the house. So this is kind of flipped because we see the if in the middle of the statement. So the dog barks because the stranger walks by the house, right? So we can actually do our hypothesis, and then the conclusion will be over here. The dog will bark if a stranger walks by the house. Number 5, this one does not have an if in it at all, so it's kind of a little tricky. All lawyers have to pass the bar exam. So if we rewrote it as a conditional, we would write it, if you were a lawyer, then that meant that you passed the bar exam, right? So our hypothesis would be that you were a lawyer, and the conclusion would be that you passed the bar exam. So you don't have to write the hypothesis and conclusion. You can write H and C if you want, or just underline once and underline twice, really however you want to do it. Not that big of a deal, but they shouldn't take you very long. All right, number 7, it says write each sentence as a conditional statement if and then format. So a regular pentagon has exactly 5 congruent sides. So that tells us if it is a regular pentagon, then it has 5 congruent sides. So our hypothesis is that it's a regular pentagon. Our conclusion is that it has 5 congruent sides. So most of the time you're not actually going to switch the order of them, so try it out, see if it makes sense if you just put an if in the front and then a then for the second part of the statement. Alright, so write a conditional statement that the Venn diagram illustrates. So here we're seeing that Italian is a subset of the Romance languages. So there are other Romance languages that are not Italian, such as French and Spanish. Alright, so Italian is a Romance language. We see that, right? So there's 2 options. It's either if it's Italian, then it's a Romance language, or the second option, if it's a Romance language, then it has to be Italian. So clearly, this option is not going to be true, because there are other Romance languages that are not Italian, so that's not always true. But if it is Italian, it is a Romance language, because Italian is a subset of Romance languages. Another way you can remember is that it is going to be P implies Q, so P is a subset of Q. So if we have this here, Italian would be our hypothesis, and our conclusion is that it would be a Romance language. So if it is true that it is Italian, then it is also true that it must be a Romance language. So that's how you would write it out, no big deal. Alright, number 15, rewrite the statement as a conditional, then draw a Venn diagram to illustrate the statement. So we'll just fill in the Venn diagram, you don't really have to draw it. So all squares are rectangles, so if it is a square, then it is a rectangle. Then the only question I have is, does the square go as a subset, or is that the big one? So squares are a subset of rectangles. A rectangle means, actually, I'll go ahead and teach you that, it's kind of fun. So in the German language, recht, which is spelled R-E-C-H-T, is the German word for right. I'm going to have to, because I know my face is going to be in the way. But anyway, it's for right. So if you look at right angle, rectangle literally means right angle. So it's a geometric quadrilateral, or a geometric figure with 4 sides that has 4 right angles, or 4 congruent angles. So that's what it takes to be a rectangle. Does a square have 4 right angles? Yes, it does, because a square is nothing more than a special rectangle. So if we take a rectangle, and it is a special rectangle that has 4 congruent sides as well. So 4 congruent angles and 4 congruent sides. If we take a rectangle and we smash it down so that all 4 sides are exactly the same, then it is now a square, which is just a special rectangle. So squares are a subset of all the rectangles. You can have rectangles that are not squares, but if it's a square, that means it also has to be a rectangle, which is kind of cool. So that's how you would draw that out. Say the counterexample that proves each of the following conjectures are false. So all the following statements in this section are all going to be false. All you have to do is find an example that proves a statement false. So when we're doing that, we're finding a proposition that is true, but the conclusion is not true. So the sum of a negative and a positive number is always negative. So I need to get an example of a negative and a positive number that is not negative. Okay, so that's going to be how I prove a counterexample that proves this statement false. So I need a negative and a positive number that add up. A sum means it's addition, right? So that add up to give me a number that's non-negative, meaning positive or 0. So one example is if we have a big, see the font's big, if we have a big negative value plus a small positive value, then our answer is going to be negative. So that would be when this statement is true. So sometimes it is true. But what happens when our positive value is bigger, see the font's bigger, it's so bad. If if our positive value is bigger than the negative, then our answer is going to be positive. So this is one case that would be a counterexample. Now, I would prefer you specifically give me an example, like -2 plus 3 is equal to 1, and 1 is not negative, right? But if we did it over here, -3 plus 2 is equal to -1, this would not be a counterexample because that actually is an example of when the statement is true. So to give a counterexample, you have to give me an example when the hypothesis is true, but the conclusion is not. So another one also is when A and B are the exact same size. So for instance, for example, if we did -2 plus +2, that would be equal to 0. And 0 is technically non-negative. It's non-positive as well, but we just say it's non-negative. So this would be a counterexample as well. Just give me one example. We'll be just fine. All right, number 21. They say all quadrilaterals, which are figures with 4 sides, are rectangles. Do they have to be rectangles? Do they have to have 4 right or rectangles, right? So this is a rectangle. That would be a quadrilateral, right? Quadrilateral could be a square. It's still a rectangle. But what about a rhombus? So a rhombus would be our counterexample because it is a quadrilateral. It does have 4 sides, but these are not right angles, right? Nope. Those are acute or obtuse angles, and actually technically both. Alrighty. Look at 26. The product, which is when we multiply, of two numbers is always greater than their sum. So when we multiply two numbers, it's always going to be bigger than if we add the numbers together. Now, almost always this statement is true. So for instance, 2 times 3 is 6, which is bigger than when we add them together, 2 plus 3, which is only 5. But this statement is not always true. Can you give me an example of when it's not true? So think of some other numbers that when we multiply them, it's not going to be bigger than when we add them. So they could be equal or they could be less than. Just has to not be greater than. So hint, hint, usually funky and weird stuff happens around 0 and 1. So think about what happens if you use 0 or 1 and one of those two. And then just come up with two numbers that prove it wrong. So this is not a counterexample because this is showing that sometimes a statement is true. But it's also not always true. So give me an example that proves this statement false. That's what a counterexample is. All right, number 27. The conditional statement says that if it is a right triangle, then it has 3 sides. So we want to write the converse, the inverse, and the contrapositive, and then we want to evaluate the truth value of each statement. So we'll do truth value at the end because we have our little trick. All right, so you don't have to write complete sentences, and you can type on the PDFs instead of writing it out by hand. It might be easier if you have a keyboard just to type some of this stuff out, and it'll be better than your handwriting. But I don't really care. Either way you want to do it. It doesn't bother me too much. All right, so converse. Remember, shoes on the wrong feet. We're going to switch the order. We're not negating it, we're just switching the order. So if it has 3 sides, then it is a right triangle. So you could say if 3 sides, then right triangle. You can even abbreviate. You don't have to use complete sentences. I just will because I typed it out, it didn't matter. All right, in inverse, so we keep the order the same. Now we're just going to negate both of them. So from our conditional, if it is not a right triangle, then it does not have 3 sides. And sometimes you have to do some funky stuff with the grammar, just, English. All right, then the contrapositive, remember that's our longest one. We switch the order and we negate it. So we're going to say if, we're going to start with the quotient now. So if it does not have 3 sides, then it is not a right triangle. All right, now that you've written them out, or I've written them out or whatever, the last thing we want to do is evaluate the truth value. So go ahead and do this. So if it's a right triangle, does that mean it has to have 3 sides? Yes, because it's a triangle and all triangles have 3 sides. So this is true going in this direction. So that would be true statement. So right off the bat, if the conditional statement is true, which one of the other ones has to be true? Remember that one? The contrapositive, because the contrapositive and the conditional are logically equivalent to each other. You're saying the same thing just in a different manner, which is kind of cool. So right off the bat, I know this statement has to be true as well. Well, let's look at it. If it does not have 3 sides, then it cannot be a right triangle. That's right, because if it's a right triangle, it has to have 3 sides. So just logic. Isn't that beautiful? All right, now let's look at the converse or the inverse. Remember, these two are contrapositives of each other. So the contrapositive of the converse is the inverse, and the contrapositive of the inverse is the converse, which is kind of cool. I mean, they are logically equivalent as well for the same reasons that our logic follows. There's so much logic going on right now. I love this unit. All right, so if it has 3 sides, then it is a right triangle. All right, so if it has 3 sides, does it have to be a right triangle? No. So that's because right triangles are a subset of all of the kinds of triangles. So all of these have three sides, but only the right triangles are right triangles. It could be an acute triangle, could be an obtuse triangle, so this is false. So instantly, what do I know about the inverse? It also has to be false because those two are logically equivalent. They're tied together. If one of them is equal, so is the other one, just like the conditional and contrapositive. And let's go ahead and look at it. So if it's not a right triangle, that means it does not have three sides. No, that's not true, because it could be an acute triangle or an obtuse triangle, and then it would have three sides. So both of those are false. And I think that's it. Awesome. Almost came in under 30 seconds, but we did some announcements at the beginning. I'm excited that we're going to be able to get through this. If you guys have any questions, I would love to go over this stuff more. We will, of course, with biconditionals tomorrow, and law of syllogism and detachment on Thursday. But if you do have any questions, remember we've got our live office hours from 11 o'clock to 12. So take advantage of those and get all of your questions answered. I'll see you guys later. Bye.